Alright, going to have a look at structure of glucose and maybe clear some things up. I don't know, it might make this even more complicated, but this might help you get your head around the structure and why it has this particular structure, and help you perhaps remember it a little bit more. So glucose is a hexose, C6H12O6, same chemical formula as fructose, which is another hexose. It's an isomer of glucose, if you like. But we have these two forms of it, alpha and beta, okay, which look very, very similar. We'll look at the differences in a second, but one thing that isn't made clear is that there's a linear form of glucose. Now, this just means the molecule itself sits in a kind of line. If I draw it out, we'll put our carbons, 1, 2, 3, 4, 5, 6. So it's 6 carbons like this, and then on one end we've got a double bonded oxygen. That's just going to be hydrogen coming off here, and then we've also got our other oxygens, which are like so 1, 2, 3, 4, 5, and then on here we've got our last one. Okay, now why have I drawn it like this? Why haven't I put why are all these OH groups on one side? Why isn't that one down there? And it looks a bit sort of arbitrary. Why have I put it like that rather than any other way? Well, sometimes it helps to look at something in 3D. So this is the 3D model of it. You can see there the double oxygen bond. There's a double oxygen bond. Our blacks are carbons, obviously. What I've done, I haven't put many of the hydrogens in just to keep it a bit easier. You can see the OH at the end, just to round things off. What molecules will do is they form a stable shape. So what's happening with all these oxygens here, which remember would be an OH group, they try to get themselves as far away from each other as they can to remain stable. So that shape that we've got there, it's actually, let's move this around a little, let's just get a slightly different shape on it. So we've got something like the double bonded oxygen, then the OH group, the next OH goes down, and so does the next one. Now notice that these bonds can rotate, okay? Now if I rotate them around a bit, we've kind of evenly spread out all our oxygens, okay? If I rotated it all that way, they start clashing with each other, they start bending into shapes they don't like. So they try and arrange, well, they don't try, they're a molecule, but they arrange themselves so that they have the most stable structure. And that's pretty much the most stable structure. That's why these things end up on the side they do. Now you won't have to remember this linear structure, but the reason I'm putting it in here is that with glucose molecules, it can flip between the alpha form, the linear form, and the beta form, and it can move between these different shapes, and in fact it does. The alpha and beta form really are present when you dissolve it in something. So when it's in a solvent, which is usually going to mean water, then that's when we start to think of the alpha and beta forms. Now actually the beta form is the most stable. So we'll look at that in a second and see maybe why. But I'm going to jump back to the alpha form first of all. Now the way it's easy to remember this is a structure, I think those little scooters that people have where they have kind of 2 wheels at the front and then 1 wheel at the back, and think of that as that little tricycle, okay? And imagine it as a fish. There's our fish on one of those little tricycles with 2 wheels at the front and 1 wheel at the back. Okay, there's my fish. Give them a smiley mouth. Now if you can remember that structure, you can remember alpha glucose, because what I've really drawn there's our eye, is this. Now I've got an oxygen or an OH down there, and another OH down there, and another OH at the back, and there's my little tricycle shape. Okay, where's the other oxygens? Well, the other oxygen actually sticks inside there, so that's 1, 2, 3, 4, 5, and then I've got a CH2OH group sticking off the top. Okay, but that is my alpha glucose. Now I've drawn it that way again just to help us remind ourselves of what it looks like. you know, in reality again, because these molecules are trying to become stable shapes, you know, it'd be a bit more like that, perhaps. Only, let's see, it's too much. So, you know, sometimes we draw them, these shapes we draw, they're not the actual shape the thing forms, it's just a convenient shorthand. But this bit down here is the key. Okay, having that's not very good, is it? It's rubbish. This group here, having the OH down at the side, means that you can put these things together. Okay, so you can polymerize them. Now in the beta glucose, I'm sure we know this, but it's the same structure, so I'll do it this way this time. Except we've got an OH group on that side. Okay, the rest is exactly the same. Now the way I've drawn this, so there's I should have drawn a different colour, but never mind. There's our beta glucose, and this is the one that would form starch when you polymerize it. This would form glycogen. Now when you look at the structure of it, the way I've drawn it here doesn't easily show you it in a three-dimensional structure, but if you do look at it in a three-dimensional structure, these two OH groups kind of sit above the ring and these ones sit below it. So it's a bit more balanced as a structure, and that means it's more stable. Okay, so beta glucose is the more stable form. You might say, well, how on earth does alpha glucose ever form? It depends on lots of things, like what's the liquid it's dissolved in, the pH, all kinds of stuff. But it does form. But beta glucose is the most stable. Why is it that shape? Just because, think back to this thing, you know, that's the way that it can get the most balanced chemical shape, if you like. So that's why it has that structure. Just to quickly run through the bonding. Let's see, it's green. The carbon atoms, and I won't put them all on, excuse me, are numbered, coming clockwise from here: 1, 2, 3, 4, 5 and 6. So in alpha glucose, the OH group from there is binding onto, crashing into my fish, is going to bind onto here. The key to it, I suppose, is to always be looking for, it's going to be the same in the other molecules we'll look at in another video, look for OH groups next to each other. They're going to bind together, and this is going to be a condensation reaction. It's going to release water, so we're going to lose one hydrogen and oxygen and another hydrogen, and these two things are going to join. Not a very good drawing, but you get the idea. There we go, like so, and we can keep this going on and on. Okay, so that's our glycosidic bond between alpha glucose. With beta glucoses, because you don't have those two OHs together, let's use a different colour. There's beta glucose, so it would look like that, but on the other side you'd have that. So our two OH groups are not next to each other. So what happens is this is basically flipped that way, so that oxygen is now in that position, if you like. It's flipped over and the two OHs will be together, and you get this one direction, one in the other direction, over and over and over again. And because of these OH groups, when they form the glycosidic bond, being on opposite sides, so you'll have one on that side and then the next one, if we can draw this properly that way, there we go, that's kind of working. You get hydrogen bonding. It's not between the glycosidic bonds, but it's between this OH bit that sticks off the top. Where are we? There. I'm sorry, there. And it just means that you can get more of these things stranded together, put together with hydrogen bonds formed between them, making it very, very strong. Cellulose, as we know, is a pretty strong structure. But that maybe has helped sort of explain some of the idea behind why glucose has this particular structure and why it forms the shapes it does.